stuff tagged on here, so let's just make it an arrow instead, so I'm not saying things are equal that aren't actually equal. Now multiply this by 5, negative 6. And what do I get? 5, 0, plus negative 3, negative 3. And I really hope this is what I'm trying to get, to negative 3. Math worked, yet again. So it's like a miracle. Okay. So I crammed in a bunch of examples today. Let's try to generalize. These are specific cases. Let's look at the general case. Just imagine if I had somebody that would erase the board for me. How much time would I save? Like 1 minute, a whole minute. Okay, so if we say that we have a basis with n elements, and when we get the representation of a vector with respect to that basis, so what are the coordinates? What are the things that I need to multiply by each of the elements in the basis in order to get x? What linear combination of them am I looking at? C1, C2, dot, Cn. These are my coordinates. If I take the elements of my basis and I stack them into a matrix, which I'm going to call P, B, I believe this stands for projection. We're going to project something into our the space spanned by our basis vectors. So this will be the columns B1, B2, all the way over to Bn. And what do I get? I get that this matrix times this vector equals x. You agree? This matrix times this vector gives me this element. I'm going to write that. B times the coordinates of x with respect to b just gives me back x. This is what we did in that first example, right? We took the coordinates and we multiplied them by the basis vectors and added everything to get the original number. So, let's consider a situation. Let's say x, b, well, no, here, n vectors, or n columns. Our matrix has n columns. Let's suppose that what we're actually getting, so this is going to be an element in Rn. Let's suppose that x itself is also an element of Rn. In this situation, what are we doing? We're taking things from Rn and we're representing them with some basis to give them representations as something else in Rn. Unless we're using the standard basis, in which case we're getting the exact same thing. So if we use the standard basis, we're representing an element with itself. If we use some other basis, we'll end up with something else. So what happens in this situation? Well, what we get here is that these are n vectors. Because they're elements of Rn, they have n elements. Right? So these are, there's n vectors, length n, and so this is an n by n matrix. And we know these columns are linearly independent. So this is an n by n invertible matrix. In this special case where we're looking at a basis of Rn, we know it has, well, we're saying it has n elements. And actually we proved that. For the case of Rn, we did this before, right? We said that you can't span Rn with less than n elements. And if you have more than n elements, then it will be linearly dependent. So we already said that. So we know there are n elements in the basis, and we have, or there are n vectors in the basis. And we have to go. So this is an n by n invertible matrix because they're linearly independent. And so what we can do is we can actually multiply on both sides by the inverse. Here, and give some room. And the inverse x. When these two multiply together, it just becomes the identity matrix. And so on this side, the identity times this is just this. And what I get is that the representation, or the b coordinates of x, the representation of x with respect to that basis, is given simply by the inverse x. Any questions about this? So this allows us to take a vector in Rn using the ordinary representation, it's just a list of numbers, and then figure out what its representation is with respect to some basis. So we have some basis of Rn, this multiplying by this matrix here transforms it into a representation. This transformation it's a linear transformation because it's given to us by multiplying by a matrix, right? And it is, what do I want to say? I mean, we know it's invertible because the inverse would just be multiplying by PB. That's what we did in the original example. We multiplied on this side to go back. So we can go back and forth. But we also have that from the big list of things that are equivalent in the theorem about invertible matrices. We have that this mapping is one-to-one and onto. So the transformation that goes from x to the representation of x with respect to the basis b, the b coordinates, is one-to-one and onto. Otherwise known as a projection. And I'm just going to throw in, although we already said this, it's linear as well. So this takes elements in Rn and matches them up perfectly with other elements in Rn. There's a one-to-one correspondence between all the things in Rn before we do this mapping and all the things in Rn after we do this mapping. And it's linear. Now the book, they say, well, they just kind of state it. I guess they don't really give a proof, which is kind of unfortunate. I guess they don't really give a total definition. This type of mapping, I'm going to write this as a definition. So if you remember, the special thing about vector spaces is their operations The operations in a vector space are scalar multiplication and addition, right? And a linear mapping is something that preserves that structure. So when we map from one vector space to another vector space, addition is preserved. If we add things over here and then map them, or we map them over and then add them, it doesn't make any difference, right? The structure is preserved. And the same thing with scalar multiplications, it preserves the structure. So if we do this mapping and it's a bijection, it's one-to-one, we're not only preserving the structure, we're preserving the elements too. Everything only goes to one thing and everything over there is covered, right? So this is sort of like a perfect matching between one set and another that preserves all the structure of a vector space. In a way, we think of these as being almost the same vector space. They have the exact same structure and they have the exact same elements, number of elements. They just have different names. So this is if a function f from, let's call it e to g, is a, between vector spaces. So this is a function that maps one vector space to another, is linear, and projective, or one-to-one and onto. More writing, so I'm going to write that one. Linear projective. And it is called an isomorphism. Mathematicians really like naming things with extra Greek words. Iso meaning same, morph meaning shape or structure. So this is a map that preserves the structure between one in one direction and in the other. It's an isomorphism with respect to the properties of a vector space. So they're vector spaces. And U, V are all isomorphic. So some examples of this. So, the mapping, what should I call this? Okay, so let's just say it takes x to its representation. So it takes some element in Rn to its representation with respect to the standard basis, which is just itself, right? It represents the element as it's with itself. This is an isomorphism. Between Rn and Rn. And it's kind of the trivial isomorphism. It's saying these two things have the same structure by just them being the same thing. This is a trivial isomorphism. Now everything is isomorphic to itself because, well, it obviously has the same structure and properties as itself. And mapping from x to some other basis, representation with respect to some other basis. both of these things being in Rn again. This is another isomorphism. So it shows that there's other ways that we can shuffle up the elements of Rn, right? We can swap elements, do some kind of permutation of the elements of Rn, and still get the exact same vector space structure. So that's what that gives. Let's give a less obvious example. Nope. Come on. There we go. P2. So this was the vector space of all polynomials at most degree 2. I'm probably running out of time. About 2 minutes. So we've got time for this. The standard basis in P2 was 1x squared right? And so if I want to represent a particular polynomial, p of x equals a0 plus a1x plus a2 squared. How would I do that? Well, the representation of p with respect to the basis b is simply a0, a1, a2. Again, I feel like the book doesn't give enough details on this, so you may have to just take my word for some of this. It's not completely precisely written and proven, but this is an element of R3, right? We can take an element of P2 and we can transform it into an element in R3 by figuring out what its representation is with respect to the spaces. We have an element of R3. We can just do the transformation that multiplies each element by the corresponding basis vector. And we're thinking of these as vectors now because we're thinking of this as a vector space. Then that particular linear combination of these elements of the basis gives us back to P2. This mapping is linear. It's bijective. Right? There's a bijection between these two things. There's a linear mapping. And so this is an isomorphism. And so what we get is, this is kind of the fancy symbol that we use to represent isomorphism. P2 is isomorphic to R3. Now I know it must be 150 now. I'm going to, this is like, attendance is optional already, but we'll try to work another example. The power of an isomorphism is that we can go from a space like P2, we can transform all of the questions that we have about P2 into questions about R3. And in R3, we have the advantage of being able to write these things as matrices and do the row reduction algorithm. So here's an example of doing that. Polynomials 1 plus 2t, 4 plus, let's use x. I don't know why they came to both. 4 plus x squared, and 3 plus 2x. Are these linearly independent? This would be hard to deal with if we thought of these as polynomials and we're trying to do polynomial arithmetic, multiplying them by things and adding things up and collecting like terms and so forth. However, we can do this in a very, very simple way. We transform these things into elements in R3. What will this one be? This one will be 1, 2, 0. This one will be 4, 1, 5. This one will be 3, 2, 0. And now the question becomes, is this thing invertible? Are the columns of this linearly independent? That's the same thing as saying, is this invertible? Right? Now, I can go through the row reduction algorithm. That's one advantage that we have now, because we have a matrix of real numbers. But I don't have to do that. I can compute the determinant instead. I'll go along this bottom row. All I need to know is that if it's 0, so actually I don't even care if I get the positive and negative part right. I'm going to take this 5, and that's going to allow me to ignore that row column. So it can be 5 times the determinant of this. 1, 2, 3, 2. I'm doing the determinant. In fact, again, all I want to know is if this is equal to 0. So I don't even care that I'm multiplying by 5. Less computation. 2 minus 6. I don't even have to write down what that actually is. Don't even do the addition. I know it's not going to be 0. It's not 0. So the answer is yes, they are independent. There's 3 of them. They're linearly independent, and well, we haven't quite got to the point where we can say that that means they're a basis. But you might think with just a little bit of reasoning why that would be true. But in fact, this forms an alternate basis for. Actually, I keep going. This is going to be the last thing, I promise. Going back to what I said here, the fact that what am I trying to say? This matrix is invertible. The columns are linearly independent. The columns span R3, and they're linearly independent. Those were 2 statements that were equivalent to saying that this thing was invertible. Well, those 2 statements are exactly the definition of the columns being the basis for R3. So that means these columns are a basis for R3. But because these spaces are isomorphic, we immediately get the corresponding statement over here in P2, which is that these 3 elements span P2 and are linearly independent. So that's you see immediately how powerful an isomorphism is. We take something that's really complicated, well, looks complicated, maybe it's a little intimidating to look at, and we turn it into something that we're very familiar with. So that's it for today. I'm going to stop.